I am live. I don't think anyone's seeing this. I looked in the wrong folder. Okay, I'm better now. All right. Shoot. So this is what the other side of my office looks like. Howdy, folks. For those of you who are just finding this stream, my original stream, there were some technical complications, and so I had to switch over to a different computer. And as I found out while I was doing this, uh, I um, I could have done it on my Linux box. The file was there. I just was looking in the wrong place. But anyway, howdy all again. Georg, Judy, Norm, Clive. Okay. So let's get on with this. All right. So again, what are we gonna talk about? What we're talking about is planetary geology, and I'm going to go through this. I think of PhD Tony. I'm thinking of PhD Tony's reaction to this lecture, and thinking he would be very, very dissatisfied with it. But I'm going to give it my best shot, get it as deep as I can, without my usual depth of things. So, like I said, I'm going to be talking about the interiors of terrestrial worlds, excuse me, using the Earth as our prime example. So, really, what we're going to do is the next lecture that I'm going to be doing, or the next lecture, which will probably be, I don't think I'll do it over the weekend, be on Monday. That is going to be strictly speaking about planetary surfaces. And there is definitely a connection between those two. Because what we see on the surface of the world, some of that is due to surface or outer space influences, such as cratering. But a good portion of it, particularly on the Earth, is due to what is happening inside of our planet. Um, Obviously, what I'm referring to is geologic activity. So the last thing I'm going to be talking about is magnetic fields. How are the magnetic field on our how is the magnetic field on our planet generated, and why is it that we seem to be the only one that has a magnetic field of the four terrestrials? Howdy, Jeff. So what? So again, the when I talk about terrestrial worlds, I know it says planets there, but really I want to say terrestrial worlds because really what I'm including the moon in this, and I guess my Professor Parks's definition of world is something that is spherical under its own weight or under its own mass. So I'm going to be constantly referencing Mercury, Venus, Earth, the Moon, and Mars in this and subsequent lectures. So when we look at the surfaces, we obviously see to a certain extent, a fairly wide range, or actually, let me back that off and say that the Earth is definitively the oddball. There is commonalities between all of them. On all of these worlds, you can see evidence of cratering. As you can see, with the moon is the famous example of it, I suppose. There's meteor crater on the Earth. Venus even has craters, although they're not quite as common. Mars has cratering. Mercury obviously has cratering. Mercury and the moon really look similar, and we'll talk about why that is later on. And there are also other similarities. You can see volcanoes to one extent or another on all of these worlds. You can see canyon features or scarps or cliffs, things of that nature. You can see what we would refer to as tectonic features on all of these worlds. The difference is the number of these features that we see on any particular world, and yeah, well, that's basically it, actually. Oh, and the sizes of the features on these worlds. That allows us to basically constrain what the geologic activity of the world is now, and what has it been in the past. So how do we know what's inside the Earth? And really, I said before I was going to talk about multiple ones. What really I'm just going to be talking about one, and that is seismic waves. Waves that are caused by earthquakes or moonquakes, Mars quakes, Venusian quakes, mercurial quakes. I don't think those exist anymore. But this works to a recent debate Toon had with Marissa. Yeah. I recently just had a rant about stuff due to that debate. But anyway, seismic waves. So a seismic wave is something that is set off by an earthquake or a violent event, typically speaking, where the two plates slip with relative to each other suddenly, and that will cause basically that will release a lot of energy, and then that will propagate or cause a wave to propagate through the Earth, not just through the surface, but also into the interior. And seismic waves come in two varieties. You can either they are P waves and S waves. I have seen them called primary waves and secondary waves, but I much prefer pressure wave and shearing wave. To me, it's a more physical description of what's going on. So with a P wave is what we refer to as a longitudinal wave. It's very much like a sound wave, in that you take a slinky, which I have. If you're a fan of the channel, you know that I have a slinky. So basically, that's a longitudinal wave where part of the wave is compressed and part of the wave is what was rarefied or is expanded. But the entire wave is straight. So the motion of the wave is in the direction of propagation, of the wave's propagation. So if the propagation is forward, then the motion of the wave is forward and back, as opposed to a transverse wave, which is kind of like that. Transverse wave is a water wave or a light wave, where you have the motion of the body, the motion of the wave is perpendicular to the propagation. So if with water waves, if you were to take a toy boat, put it on a still pond or lake or what have you, and then somewhere else drop a rock to set up waves, the waves would propagate outward. They would propagate underneath the boat, but the boat would, for the most part, go up and down. Obviously, there's a frictional component, so it will shift over a little bit, but primarily its motion will be up and down. That is a transverse wave. Now, why am I talking about this? Because of the properties of both of these waves in terms of what kinds of medium they can propagate through. So pressure waves can travel through solids and liquids. Well, they can travel through solids and liquids. I was going to say travel through solids and liquids just as easily, but that would be a lie. That would be wrong. But pressure waves can travel through solids and liquids to one extent or the other. S waves, however, can only travel through solids. And so modern geologists are able to, when they put up seismographs, they can determine what kind of wave they're receiving. They can tell if they are getting a signal from a pressure wave or a signal from a shearing wave. Oh, hey, Gary, you're in the house. Awesome. Um, more? No, actually, I'm not going. I'm not going to be talking about fairy tales. Although I just now have a sudden urge to watch the Hansel and Gretel movie with Jeremy Renner and I just lost her name. Anyway, with Jeremy Renner, awesome movie. If you haven't seen it, I highly recommend it. So when you look at this, so the in this case, if we go back, you can see on the upper right above the P waves, you have a yellow line with red dots in it, basically red dashes. So that's to representing the compression and the expansion of the wave, whereas the S wave is a squiggly. So if you look at um, this particular diagram, what you can see is that uh, when a um, when a earthquake pops off, say up here, that wave is going to propagate outward. And so here, the S wave is going to basically continue until, well, will continue in effectively a straight line. It will deviate a little bit simply because the density that it's going through is actually varying, but it will go relatively straight line so long as it doesn't encounter a liquid or semi-liquid, semi-fluid substance. At that point, it's going to stop. Whereas pressure waves will continue to propagate through such a material, but they will be highly refracted and they will move. So depending on, so the way that seismologists do this is, I thought I had a better example of this. I thought I had a better image or a better cartoon of it. But when you have seismographs all over the world, you can then you will see basically where you can pick up if you know where the earthquake happened, you can then see the pattern of, all right, over here I'm going to be able to pick up P waves and S waves. Then you're going to get what's known as uh, a shadow, where you're not getting anything, and then down here you're going to be able to get P waves. The only way to explain that phenomenon, the only way to explain that observational evidence of seeing P waves and S waves together in certain locations, but only seeing P waves in other locations without shearing waves. The only explanation for that is that part of the core or part of the interior of the Earth is in fact liquid. Now, on top of that, how do we know that there are different layers? The reason why we have different layers is because they are of different densities. Again, this is why my friend really hates these sorts of things, because this is an oversimplification to say that the mantle is of a density and implying basically a homogeneity or a homogeneous uh, density. But we're going to go with it. It's for ease of explanation. What we can see is that there are effectively four um, four layers to the Earth. There is the crust, the upper crust, which is relatively thin. It's maybe a few tens of kilometers in size, which is of the lowest density of material. Then you have a mantle region, which has a slightly higher density. And then you have a core, which is differentiated into two layers. You have the outer core and the inner core, which is composed of the densest materials, iron and nickel. The lithosphere I'll explain in a moment. So over here we can see that the core is iron and nickel, mantle is silicon iron or silicon oxygen, and the crust is like granite, basalt, or aluminium for all you Brits out there. I do want to take one moment and say, yes, I hope Bob Donnell is with God. I hope he rests in peace. He may have believed that the Earth was flat, but he was an experimentalist. He was a seeker of truth, and for whatever he was, I wish him well in the afterlife, and I wish his family nothing but. I wish them well in this time of sorrow. So, with that out of the way, well, not out of the way, I do. That reminded me. Thank you, Norm. I did want to mention that, talk about or mention Bob Nodell's passing today. So why is it that we see this? Why is it that we see a crust of less dense material followed by a lower down mantle of medium material, and then a core of really high density metals? And I mentioned this before in terms of asteroids, and what this is called is differentiation. Differentiation is the process via which denser materials, if you have a sufficient amount of mass in a volume, then two things are going to happen. The self-gravity between each basically little bits of material, technical term, the gravity is going to form that object, regardless of what it started initially. It's going to form that object into a sphere. And then on top of that, it's going to cause differentiation. If that material is made up of different materials, if that body or chunk is made up of different materials, the materials of higher density are going to experience a greater gravitational effect, and they're going to be pulled downward more than material that is of lighter density. And the bigger or the heavier density material is going to bully its way down. It's going to push out all the lighter material, and that lighter material, because it's being displaced, is going to just move upward. So, oops. Did I miss the lithosphere? Yes, I did miss the lithosphere. The lithosphere is very important in terms of understanding something I'll talk about next time, which is plate tectonics, or really tectonics in general. So the lithosphere is this solid, semi-fluid layer that incorporates the crust, the rocky crust, the solid crust, and a little bit of that molten mantle beneath it. Depending on the thickness of that lithosphere is going to tell you whether or not your planet or your world is going to have plate tectonics or simply just tectonics. And what I mean by that is that it's going to let you know if the lithosphere is thin enough, then the interior actions of the world, inside the world, the magma moving around due to convection of heat, that's going to cause a lot of strain on that lithosphere. If that lithosphere is thin enough, that strain is going to cause that lithosphere to crack into plates, what we call tectonic plates. If the lithosphere is thicker, then obviously it can withstand more of a pressure, more force against it that's trying to rip it apart, and it's going to stay solid. The lithosphere is basically solid. It's not molten really at all, or not really. Again, hand wavy. But the thicker the lithosphere, the more solid that it is, and again, the more tensile strength it has to prevent it from cracking into plates. Okay, my slides seem to be going weird. All right, so why are big planets round? Well, what this tells us is that, as I said, why they are round, why the Earth is a sphere, why Mars is a sphere, so forth and so on, is because of self-gravity. The way that gravity, the directionality of gravity is just going to settle things of sufficient mass, meaning that there is a sufficient enough gravity to cause this effect. It's going to arrange that mass into a spherical distribution. Now, as I've mentioned, there's some interior motion inside the planet. When the planet is first forming, it's molten, and it's got a lot of difference in temperature in different regions. It's going to cause material to move in different ways. It's going to cause a lot of stress. Now, why the Earth or why the world stay round is because this is a fairly slow process, at least comparatively speaking. If the example is silly putty, if you take silly putty, which is malleable, and if you just pull it apart suddenly, you can break it into two halves. But if you slowly pull it, then that material can be manipulated into another shape. And so when these planets coalesced, they coalesced relatively slowly, as opposed to violently just crashing into each other or breaking apart. So what causes geologic activity? You know what? I keep thinking I missed a slide. There it is. That's the slide I missed. When we look at planetary interiors, again, we see a vast, or we see a lot of similarities, and we can see this based on various measurements, based on various satellite measurements that we've taken around all of these worlds, or measurements of their mass and their radius and their densities and so forth. With the Earth, as I've already described, you have the crust, you have the mantle, you have the interior core. With Venus, it's almost identical. You have a crust, a mantle, an inner and outer core. The difference is that Venus's lithosphere is just slightly thicker, or we believe that we have evidence to suggest that Mars is lithosphere is just slightly thicker than the Earth. Mars, again, very similar, although whether or not it has a liquid core is still an open question. It may, in fact, just have a solid core. Probably does, and I'll get to why that is in a second. But we know that the lithosphere is much thicker, and I'll explain why, again, in a moment. Mercury, as I mentioned in the last lecture, and this is a gross exaggeration, this is not to scale in any way, is that Mercury has a crust and a very, very small amount of mantle material and an oversized iron and nickel solid core. We suspect the reason for why that is because at some point in its formation, when it was basically just a ball of liquid hot magma, it got slammed into by a large projectile, a large planetesimal, and that stripped basically it stripped the magma, or stripped some of the Mercurian material out into space, and the rest of the material, because of gravity, coalesced back into a ball and continued its differentiation. So most of the material that was swept off by the planetesimal was in fact that mantle material, whereas the iron and nickel had already differentiated towards the center of the core. And the moon is really just an Earth miniaturized. Again, the core is solid. The difference between the moon and the other four worlds is that the moon's core is actually offset. So if you were to look at the geometric center of the moon, the core would not be centered on that geometric center. It's actually slightly moved towards the Earth. And we suspect, and one of the pieces of evidence for that is because of the fact that there are mare on the surface of the moon on the near side, but not on the far side. And when we talk about the formation of mare, hopefully you'll get an understanding of why it is that the offset core is important. Differentiation, lithosphere. What causes geologic activity? Well, basically heat. In order to cause geologic activity, as I've been telling my physics students, in order for something to move, in order for something to be active, it has to have energy, and that energy has to come from somewhere. And so there are three methods via which a planet can gain energy. There is accretion, and that is the formation process. Again, from last time, I talked about the conversion of gravitational potential energy into kinetic energy. Kinetic energy is also can be thought of as the energy of heat, and so that accretion process generates a good amount of heat. That is the primary way that worlds gain their heat. Then you have differentiation. Again, you have the more dense material slides towards the core, whereas a less dense material gets pushed outward. That that action causes friction, basically because the you can think of it as the more mass or the not more massive, the denser material sliding by that lighter material, and in doing so, it like you rub your hands together, you're generating heat in that way. And then lastly, when things cool down enough that uranium can actually exist in in a stable form or a neutral form, I guess, you can now start having, or rather, radioactive elements are formed and basically live stably. They can decay, and radioactive decay will also, as fission reactors around the world have demonstrated, radioactive decay can release, in some cases, a tremendous amount of energy. And so that is what is supplying the energy to these worlds now, ongoing, particularly the Earth. Okay, I'll get to Gary's comment in a sec. Now, what about cooling? Obviously, the Earth is not a big ball of molten hot magma, right? We have a cool crust, a relatively warmer mantle, and a very very hot core. So obviously, at some point, the crust, at the very least, has cooled off, and and also the mantle has cooled off relative to the core. So what actually causes the cooling of planetary interiors? Well, with accretion and differentiation, what we find is that, again, because of converting gravitational potential energy into kinetic energy, the farther something falls, the more heat is generated. The larger the kinetic energy, the more heat gets generated. The longer something slides against something else, the more friction is generated, and so the more heat. And so what happens is that as this world is forms, there is a temperature gradient across. The surface as it formed is going to be cooler than the center. Even though at the very beginning it's all molten hot, the core is still hotter than the outside. And thermodynamics tells us that the Earth wants to equilibrate. The Earth wants to be the same temperature all the way through. And so that energy from the core has to go somewhere, or that energy from the core has to move outward, and it does so via three different methods. It does so from the first, it does from conduction, which is conduction, which is the heat from a hot metal to a hot material to a cool material. This is how the energy gets basically passed through the interior core. Then you have convection gets set up in the mantle region, as shown, where you have hot material. You have a pocket of material that is locally hotter than the surrounding area. That will cause that material to become more buoyant and rise outward towards the crust. And as it does so, that bubble or that mass, that localized area, is leaky. Technical term, not brine leaky, but leaky. And it's going to leach energy out into its surroundings, heating that environment up, until eventually that the temperature of that blob is going to be equilibrated or be the same as with the temperature surrounding it. And then it's going to actually get a little bit colder, and it's going to start falling back down again. And then it's going to heat up as it does so, and it causes that cycle. Basically, the interior of the Earth is slowly boiling, very much like the exterior of the sun, as we'll talk about, not now, but at the end of the semester. And then finally, you have radiation. Radiation is when the energy radiates via photons from the surface of the Earth through the atmosphere and out into space. And so the planet is constantly losing energy over time. So it starts off with this initial amount of energy, this initial pot of gold of energy when it forms. It's constantly getting more energy, or some of that energy is constantly getting resupplied through radioactive decay. But but it also is, again, losing that energy via convection, conduction, and radiation. As it happens, radioactive decay is not sufficiently high enough to keep the planet the same temperature over time. So the temperature is eventually going to get colder over time. And how long will that last, or how long will that take? Well, roughly speaking, we can say that the heat content, the amount of energy, the amount of heat energy inside of an object, is proportional to its volume. Its loss of energy, how it loses energy, is proportional to its surface area. And so if you look at that ratio, what you find is that it's, if you just, again, assume that it's a sphere, it's 3 over r. You can think of that ratio as a time scale of heat loss. And so if you have a large radius, if you have a large world, that heat loss time scale is going to be much smaller than a world that is smaller. So for example, if you take Earth and you compare it to Mars, Earth is has twice the diameter of Mars, and so it's going to basically cool off half. Earth is going to take twice as long to cool off as Mars does, roughly speaking, to first order. And so this is why we see geologic activity on certain worlds and not others. Why certain worlds are what we refer to as geologically active, whereas other worlds are geologically dead. It also explains why, it's again not quite settled science, but it also explains why the Earth has plates, its crust or its lithosphere is cracked into plates, and Venus is not. It's because Venus is slightly smaller than the Earth, and so it has lost a little bit more heat than the Earth does. And so what that means is that the lithosphere has thickened. So the lithosphere has become, or is solid. So as the planet cools, it becomes solid. The liquid hot magma no longer becomes, or basically becomes rock. And so that lithosphere has gotten thicker to the point that the plates, if there ever were any, are now fused, and the entire surface is one solid crust. It also explains why, but Venus is still geologically active, and it's significantly geologically active. There are volcanoes. We actually believe that a geologic event happened within the last 100,000 years on Venus to resurface the entirety of the planet, and that is weird. And as far as I know, that is very much an open question as to why all of a sudden the entire surface of Venus was covered in lava and resurfaced itself, basically just put on a nice coat of asphalt. With Mars, as I've said, since it's so much smaller, this is why we don't see geologic activity now. We've been studying Mars for a very, very long time now, or at least, human lifespan kind of long. And we've never seen a volcano go off. We've never seen tectonic activity. There are Mars quakes that some of the rovers do have seismographs. And so They have actually detected Martian quakes, but they are very, very small, very, very slight. And so we think that we basically think that Mars is essentially geologically dead. But at some point, it was geologically active because we see surface features that can only be explained through tectonic action. We also see some very, very large volcanoes. Olympus Mons is the largest volcano in the solar system, and if you plopped it down on the Earth, it would take up the entirety of Arizona. So it has a few very, very large shield volcanoes. So Mars was geologically active at some point, and probably for a few billion years in its lifespan. But now, not so much. And it probably hasn't been geologically active or significantly geologically active for the last billion years or so. Mercury and the moon were probably only geologically active for 100,000, 100 million years, or basically 100 million years or less. That's kind of my wild scientific guess at this point. The main point is that it's very, very short. Mars or Mercury and the moon were geologically active for a very, very small fraction of their lives, but we can still see things like dormant volcanoes on the moon. We can also see things called rills, which are indicative of lava tubes underneath the surface that have collapsed. Lava was in them, but is now become solid, and the whole thing is collapsed. Mare, those dark stains that you see, were due to volcanic action, or rather tectonic action. And so Mercury and the moon were geologically active, but are most certainly geologically dead at this point. So, why do planetary interiors have magnetic fields? Now, I'm going to rank the magnetic fields of these worlds in terms of strength. You have the Earth, which has the most magnetic field, which has the strongest magnetic field of any of the 5 worlds. And it's not, in comparison to Jupiter, it's nothing. Comparison to the sun, it basically it might as well not exist. The magnetic field of the Earth is not very strong at all. The next one coming in, oddly enough, is Mercury, and then you've got Mars and Venus, and then you've got the Moon. Now, this goes into, so why is that? Why is it that the Earth has a significant magnetic field, and the other ones really don't? And Mercury has a magnetic field that is non-zero, but I really wouldn't consider it significant. Good question. Would the greenhouse effect be helping Venus to keep more heat in the core? That is an excellent point. In that, yes, it would prevent it. It prevents, to a certain extent, it inhibits the radiation of heat outward, but at least initially. But at some point, it's going to equilibrate. Again, it's going to become, the amount of heat loss is going to stay constant based on the thick, or the, once the atmosphere settles down, the Venusian atmosphere settled down and became carbon dioxide, and basically set up a stable greenhouse effect. That's going to stabilize the heat loss, and that still is going to cause Venus to be slightly colder than the Earth. But I've never thought about this, and I've never read anything about this, but I would intuit that you are correct, Peter, that if you took a world of similar mass and similar radius, and somehow were able to strip away the carbon dioxide and have an atmosphere that is comparable to the atmosphere of the Earth, at least in density, then yes, that world would actually cool off faster than the heavily enshrouded Venus. So, nice observation. I will look into that. So, what do you need for a magnetic field, for a planetary magnetic field? Well, what you need is charged particles, and you need those particles to be able to move freely. Ideally, you also wish those particles to be moving in a same direction. Think about an electromagnet. An electromagnet works because you have a wire coming off the positive end of a battery, and you don't have to do this, but many folks do just to give it more oomph. Technical term is you wrap that wire around an iron core, and then connect that to the negative end of the battery. You now have current running through that wire. Electric current, is simply the movement of electrons through that wire. So you have negatively charged particles moving through that wire, all pretty much together. So charged particles moving. That creates the magnetic field. So again, from a planetary standpoint, way more complicated than a simple electromagnet, but we can keep with the analogy. So what do you need to achieve that? What does the planet need to have in order to have charged particles moving moderately fast in roughly the same direction? Well, need three things. You need a molten liquid outer core, or liquid region, basically more liquid than semi-fluid. Here we're starting getting into different types of exotic phases, which is way beyond the scope of this course. But let us just say that the outer part of the core is more liquid than the mantle, and so in that core, in that outer core, you have electrons. That outer core is liquid because there is more heat located in that region as opposed to the mantle. And what that heat means is it has more energy. And as we talked about with light, the more energy you have, the higher chance that you're going to excite the electrons of the metals in that outer core. And in this case, you can strip some of them away, because when you talk about heavy elements like iron, those outer electrons, you can basically sneeze on them and they will fly off. So you'll have a whole bunch of free electrons, what we call free electrons, in the outer core. Now you need to get them moving. Now, one thing you have convection. So you have the energy radiating off of the inner core through conduction, rather. That hits the liquid outer core. That sets up convection, which is moving particles. So there you have part of the motion. But on top of that, the whole thing swishes, in that the Earth is rotating with a sufficient enough velocity, angular velocity, that the interior of the inner core is rotating relative to that iron center, that solid iron center, kind of like the electromagnet, kind of like the fact that the electromagnetic I missed a vital point. I missed a vital point in this. A magnetic field is generated by, maybe I said this. Let me just be clear. A magnetic field is generated by the motion of charges. So, with an electromagnet, what's causing the magnetic field is that movement of that current running through that wire. The iron core, what will happen is that the magnetic field created by that wire will then induce another magnetic field inside that iron core, and it will strengthen the overall field of the magnet. And so, in an analogous sort of ishy way, timey-wimey sort of way, the outer core can be thought of as that wire moving around, creating that magnetic field, and then that is then causing the inner core to be magnetized, strengthening that field. And so that is why we believe that the Earth has a magnetic field. Now, why doesn't Venus have one, and why doesn't Mars have one? Well, Venus doesn't have one because it doesn't rotate very quickly. Again, I'm kind of embarrassed myself because I don't know the number off the top of my head. That's why I have the interwebs. But a single Venusian day is on the order of, I think, 170 days. It is exceedingly slow. The Venus, probably because of probably due to whatever it was that flipped it on its axis, it rotates very, very slowly. And so that gets rid of the moderately rapid rotation. There may be convective action going around in the outer core of Venus, but because that isn't sloshing relative to that inner core, there is no wire. There is no current running through the wire, and so there is no electromagnet, because the iron core in itself does not have a intrinsic magnetic field to start off with. Now, Mars, why doesn't it have it? Because Mars more than likely doesn't even have a substantially large liquid outer core. As I said, it's cooled off significantly more than the Earth has, and so it's become solidified down through the core. Now, it might have a little bit of outer core that is liquid. Again, definitely more study is needed to be sure of that, but it's certainly not large enough so that you have a sufficient number of electrons getting moved around the outer core to generate any kind of significant magnetic field. Again, in this case, it does actually have a rapid rotation and sort of a cosmic accident. The rotational rate of Mars is actually basically 24 hours. It's a little bit longer than the Earth's, but it's essentially 24 hours. So the Earth and Mars have roughly the same rotation rate. So what about Mercury? What about Mercury? And so here, on what I'm showing you is that a magnetic field of the Earth can be approximated vaguely. Again, my Vic is in the back of my head. You can basically approximate the Earth as a bar magnet, in that you have a north magnetic pole and you have a south magnetic pole. That electromagnet is that convection, or excuse me, that outer core motion is consistent in that it creates a bar-like magnetic field, or what we call a poloidal magnetic field. Is it poloidal? Yeah, poloidal. Not toroidal. It's basically a bar magnet. You have a north end and you have a south end. Now, it gets way more complicated than that because the magnetic field, the poles move and they flip. That we have evidence basically from rocks that the magnetic field at one point, the magnetic field at the north geographic pole was south at one point. Now it's north, so north and north. Before it was north and south. Before that, there was a period of north and north again. And so we know that the magnetic field flips, and again, not open or not well understood. Sorry, I just noticed my creamer was sitting out, warming up. Oh, no problem, Peter. What was I going to say? Yeah, so no, I've now completely lost what I was going to say. The flipping of the magnetic field. But in essence, you can think of it as a bar magnet, which brings me to Mercury. What we believe happened with Mercury is that Mercury at some point did have a dynamo. It dynamically generated a magnetic field through the motion of electric charges, and that again induced a magnetic field in the inner core. And then that magnetic field, and while essentially the current got shut off in the electromagnet, the magnetic field in the core, in basically that iron bar in the electromagnetic example, or just the iron ball that is the core of Mercury, that held on to that magnetic field. So it's a latent magnetic field. They're really, unless you add energy into the situation, that magnetic field is going to stay constant in perpetuity. And so again, and also because of the fact that it has an oversized core in relation to its overall size, that magnetic field is enhanced. So that's why Mercury has has a much more significant magnetic field than either Mars or Venus. And I think, yeah, basically, like I said, Venus and Mars don't have one. Moon had one a really long time ago. I said Mercury is a substantial magnetic field, but that is, again, not due to current geologic activity. That is simply because there is when it was geologically active, the magnetic field that was generated in its dynamo is frozen in its core. And as I just said, unless you input energy into that situation, that magnetic field is going to be stable over a very, very long time scale. And that, friends and neighbors, is my lecture on planetary interiors. And so obviously there's a 200. I thought it was 243, but I was like, no, that can't be right. That's got to be the rotate or the revolutionary period. But yeah, that's why the internet is for. I don't keep those little factoids in my head for some reason. Maybe because of my early onset dementia. I don't know. Yes, that's right. That, you know what, Peter? I am ashamed that I did not remember that. That is one of the peculiarities of Venus. The Venusian day is actually longer than the Venusian year. So, yeah, Venus rotates very, very slowly. So, all right. The new names are positive pole and negative pole, according to someone smarter than Einstein. Oh, yeah. That was if you're interested in, for those of you who are watching this at some point and are not part of the flat earth debunking community or not familiar with flat earthers, if you want an excellent example of just, yeah, alternative thinking, check out MC Tuden's channel. Check out his most recent discussion with a woman by the name of Marissa. She claims to have been smarter, or she claims to be smart. No, she claims that Einstein was a moron. Not that he was wrong. Well, that he was wrong, but that he was a moron. And that there is no North Pole, there is no South Pole, because for reasons. Check it out. If you want a good laugh, you need to check it out. All right. Anyway, so next time I am going to be talking about planetary surfaces, which is, again, one of the ways that we constrain our models of planetary interiors, is because if we see a whole lot of geologic activity, particularly ongoing geologic activity, then we know that there has to be a differentiated interior where with convective action happening inside the mantle. Excuse me. And from there, I think the rest of the semester, the rest of the coming weeks, we're going to just be kind of moving outward. We're going to talk about geology. I'm going to talk about surfaces. Then I'm going to talk about atmospheres and so forth. So, all right. Yeah. And for those of you who may have joined late, I actually started late because I was recording a different lecture. I wasn't live. Obviously, I wasn't live. I was actually recording it. I'm actually really excited about it. It is, so I have a whiteboard in my office, and I've been wanting to do more analytical sort of work, or not. That's kind of a fancy. Basically, I want to show equations. I want to do just simple algebra in terms of showing you how physics works. And so I did this lecture, which I don't know how long it is. I go through Galileo's inclined plane experiment and how it is an excellent demonstration that gravity is a thing. rather than, say, electrostatics, or rather than relative density disequilibrium. So if you have the time, either today or tomorrow or what have you, if you have the time, I would really love for you to watch it, and I would really love feedback. It is unedited, um, and I kind of like that idea because it gives a sense of, you know, I'm I'm a human being. I make mistakes, and so it's very human, I guess. And so, yeah, I would really love to hear your thoughts on not just the material itself and what I was trying to communicate, but also the style of it. Do you like the way that it was presented? Because if so, I plan on doing more of that. I plan on doing more of looking at like the simple pendulum and uh, deriving the Kepler's laws. There's also some there's also some technical aspects that I want to know, because I don't even know if people can, when they watch the video, can actually read the board that I'm writing on. The pens, from when I was my perspective looking at the screen, the pens really weren't all that distinctive on the board. So, I read off what I was writing, but I really hope that it actually comes out on the screen. If not, then I'm going to have to come up with a different camera. I was only using the camera on my Mac, but I have other cameras which are better. So hopefully, yeah. Anyway, so please comment the hell out of that. Just let me know your honest opinion on that video. I'm going to be uploading that right after I sign off here, so it should be up within the next half hour or so. So, all right. Oh, okay. All right, Norm. Yeah. Oh, I want to read before I go. I want to look at what Gary was saying. Globy world. All right. If we pretend this and that and the other thing, we can then pretend the Earth could be a spinning pear orbiting the sun that is careening through space towards some galactic center. Um, okay. Well, first off, the sun is not careening towards space to some galactic center. It actually is in a very stable orbit around the galactic center. So it's never going toward. Well, it's probably it is eccentric, so I guess you could say at some points it's going toward, but we're not flying into the galactic center by any stretch of the imagination. We are orbiting very much like a planet orbits around the sun. So spinning pear. See, this is another. God damn, Neil deGrasse Tyson. I really wish he hadn't said that, because, yeah, I guess technically it's pear shaped, but not really. I mean, not really. So, and people just hang on that. I'm like, it's not really a pear. Anyway. So that's that. Yeah, I'm gonna let that go. So yeah, all right. Gary, just basically just a, we don't, this. I've said this to you. Others have said this to you. We don't pretend anything. We gather data, which then gives us confidence in what we understand and then what we communicate to the public. So it's not pretend. So there you go. We're not just coming up with this out of our keisters. Yeah, more egg shaped. Yeah, I guess. I mean, the top is more constricted than the bottom, but when you talk about the how much it's constricted, to me, it's basically negligible. You certainly can't see it when you're in orbit. So yeah, there you go. Georg got it. The pear shape is less than 2 pixels in an image. Yeah, it's minuscule. I would argue that it's essentially negligible. But all right. Now I'm rambling, so I will I'm at the 1 hour mark, so I will, unless anyone has any questions, I will sign off. Thank you all for watching. Hope you found it educational and enjoyable. For those in the future, hope you find it to be the same. As always, like, share, and subscribe. Comment if you have any questions. Oh, and ring the bell. I keep forgetting to tell people to ring the bell because I post chaotically. So getting notified is probably the best way to kind of keep current with these things if you want to watch these lectures live. If you don't care, there you go. Just at least just subscribe. So if you want to help here us here at the observatory financially, because again we try to do a lot of outreach that requires a certain amount of financial backing. So if you'd like, you can hit me up you can become a patron. There are certain benefits at certain levels, or you can hit me up on PayPal. All proceeds go to the universe, or go to the observatory or the student club. Okay. Peace out and clear skies.